Ah, really warm applause, thank you. So I like just to introduce a funny topic. It's called mutation testing, and I'm really proud. It's many persons in the room, people in the room. Sorry. Okay, who saw this talk at Eurocamp? Ah, some hands. Okay, basically it's the same talk, but the background is now not black anymore. So that's I changed it, and I'm really proud. It's better. Okay, so I'm gonna talk about testing strategy. This testing strategy is called mutation testing, and it's hard to explain. So I'll try to not rely on slides because actually I'm not really good in creating some good slides. So I really hope you interrupt me in case I go too fast or use terms which needs explanation, because that's it. That's a setup of talks I really like. So if there is no question, I will pick random people on the audience and say, okay, what's the AST I'm talking about? Tell me. So okay, let's start. Mutation testing is about test your tests. Why should tests be tested? So we all say, okay, we write code, we do TDD, and once we have the test, green test, we can say, okay, good job, let's move on, deploy it. Yeah, it's not that easy. Okay, so let's first say, okay, I started testing years ago. I hated it. Seriously, I hated it. When I started testing, I was always freaking out. So, oh no, I just hacked for 5 minutes. Typically horse, to get something working. Now an HTML site is presented on the screen. I'm happy. I need to ship this. And then someone told me you need to test. I said no, not me. So testing, nah. Because I tested it, I ran it multiple times in my browser, so it must work. Okay, but that was before I finally got into doing TDD. Then I started to do far too much testing. I basically tested the arithmetic primitives. 1 plus 1 should equal 2, because I do not know when to stop. So I finally started testing and did far too much. I wasn't identifying edge cases. I was just enumerating everything I could enumerate because I thought this is testing. So it didn't work out. So over the time, I discovered test metrics. Oh, what a cool thing. Test metrics. Some automated way to verify I tested enough. Cool, let's achieve it. Let's try to use test metrics. So the first thing is pretty lame. So I said, okay, there is a ratio between lines of code written in test and lines of code written in code. And yeah, if it's close to some specific 1 or 2 or whatever is good, I'm done with testing because it's enough. Yeah, okay, it's a joke, so let's go. Then I saw the line coverage thing, and the line coverage thing proved pretty well. It showed me, okay, there is a nice report. Some lines are backgrounded green. That's probably because the slides are now backgrounded green, so should be. So yeah, cool. Once I see 100% coverage, I'm done. I can ship my code. Cool. Let's move. Now it's not actually really true, because there is here the ternary operator. This is a 100% covering test case. So I only have to put in a true, and only one of these branches gets tested. So it might still blow up, and it happened to me a lot. So I was the king of pushing typos, because the right side here is basically, okay, now it's a literal symbol, but it could be any mistyped method call and will blow up in production, because your users are actually fuzzing your application all the time. And if you don't have any users, Google will fuzz your application. So it doesn't give you anything. So then I did some formal research, and I found the branch coverage. Cool, really cool thing, because we don't have any tooling in Ruby, but there is well-tested code outside. We all use SQLite is branch covered, and it's basically one of the best covered library we ever will have in open source. But actually, branch coverage itself, or statement coverage, which is in my opinion the same, we can argue later, but it also has some nasty properties, because if you have 2 statements next to each other, only the last side effect, or the last semantic, the last statement generates, needs to be tested, and this side effect A does not need any confirmation it's actually intended. So it's not a solution. Then I joined the ROM team, aka Datamapper 2, aka we won't finish it, or whatever. So yeah. Yeah, and there was a guy, his name is Dan Karp, and he said, Markus, your tests suck. Try to read code I wrote, and it's mutation covered. And I said, oh my god, what's that? And I ran these tests, and I was totally, yeah, I was freaking out. It was so nice because actually mutation coverage turned out to capture all the metric values I just showed. If you apply it right, you can easily beat all line coverage problems. You can beat the statement coverage problems. It worked. It has some shortcomings, and especially the mutation tester we used at that time had some shortcomings. And so over the time, I realized, yeah, okay, I cannot simply bitch about there is a bad mutation tester because I didn't wrote it. So in case I have to fail for myself on doing that, and that resulted in the mutant project. But let's first go into a little bit more. That's a slide I will come back later because okay, I'm not good at creating slides. So let's go into some formal definition. So with mutation testing, it's not as easy to explain as line coverage or statement coverage. We need some agreement on names. So in the following maybe 10 or 15 minutes, I will talk about alive mutants and killed mutants, and a mutant itself is just a variation of your code. So if you change a literal 1 to a literal 2, the literal 2 is a mutation. That's quite easy to understand. So the problem is mutation testing changes your code in an automated manner, runs your test, and inverses the meaning of tests. If a test fails after the change, we basically count the mutation as killed, and if any change slips through the test after it was automatically introduced, then it calls as alive. And because we all know movies, so mutants should be dead. So please, so I never saw a good mutant. So, sorry? Yeah, okay, good. Yeah, I also have several specific mutations which should not be dead, but we can go into that later. Okay, when we want to mutate code, it's not about doing substitutions on strings, on the string representation of code, because you will break the syntax, you're not really sure what you're doing. So there are mutation testers outside I saw for the Go language or many other language which just grabs through the code and exchange a minus with a plus or so. That's not a durable strategy to do a mutation tester because the semantics of today's programming language, especially Ruby, are insanely complex. So you need a transformable representation. And the transformable representation is the AST. Who knows what the AST is? Yeah, really nice. So he just said the advanced Schirp transform. Okay. It was not a full coverage here, so I will just go into the AST without a slide because I don't know how to do slides in the right way. The AST is the abstract syntax tree. So if you ever saw at university, probably you saw them. It's 1 plus 1 is a plus at the top, and leave right there is a 1, and right there's also a 1. That's the AST. The AST is an abstract representation, which is the result of a parser. So if you parse code, you probably end up with an AST. If you parse Markdown, you end up with HTML. So, okay. So there is another class of mutators you could use, but I did not go this route because it would not have been portable. In Ruby, we don't have a shared runtime, we don't have shared bytecode, we don't have even have a shared AST, but the AST is somehow shareable across implementations. So I choose, let's do an AST-based mutator. This is another mutation example. Probably the slide should have been more early. So this is the same method I mentioned above about, not above, it's left, to where we had the line coverage thing. And that's interesting. The mutation tester changed that input to true, a constant. And the test we had before, which gave us 100% line coverage, it will still pass. So the mutation tester here identified a missing test, superfluous code, or whatever. So basically, cool, the missing statement was, the missing coverage was identified. So, yep, the same. If you want to kill the mutation, you basically have to make sure the other branch gets executed. So in this case, just add a new test or drop the code. So, okay. There are many ways to mutate your code. I cannot even enumerate all of them. So I tried once, but it's a deep rabbit hole. Maybe I don't understand the domain good enough to come up with that's the definite set of mutations. I still discovering. Yeah. Yes. No, also the mutation tester typically only changes the code in an automated. It tries to make the tests red. In case it cannot make the tests red, probably a test is missing, or you have superfluous code. That's the idea behind. It's 100% mutation coverage in that case. So code coverage is a little bit unspecific term. Okay, so we can do many types of mutations. We can change literals. We can just delete statements, which actually will prove a statement has a measured side effect that solves the problem with pure statement coverage. We can inverse conditionals. We can do binary connective operator replacements, change an N to an or an OR to an XOR. We can delete arguments to make sure defaults are tested, and so on. I could not even enumerate them in that format, so I just need to move on. There is some real-world use of all that stuff. We try to write ROM, the Ruby object mapper, and we try to make sure it has 100% mutation coverage. And this is some measurement from a component we have. It's called Axiom. It's the relation algebra behind it. And I just ran it today, and it did not even finish because Mutant has currently some problems on its library. So okay. Yeah, it's super slow. So it's a technique. It's a technique you don't want to run at your commit stage. I wanted to cover that stuff later, but it's actually a really good point. For each mutant, in the worst case, your whole test suite gets run. And I say your whole test suite. So if your whole test suite touches the database to set up stuff because you are an active record, you basically have super runtime. So I don't talk about horse here, I talk about days. So if you write real unit tests, mutation testing can be really fast. And if you write unit tests in a way, the mutation tester, in this case Mutant, can identify there is a unit test for that subject of mutation, it can only run these specific tests, and then it becomes quite fast. So for example, when we introduced mutation testing to Axiom, it was runtime of a day, and once we scoped the test execution to the public interface tests, it went down to 30 minutes, which is manageable. Okay, so I just simply lost the track, so I will just discover what comes next. Perfect. Okay, there is reporting. So typically mutation testers need to report the mutations in a way programmers can consume them. I choose to implement it via the diff because we all know how to consume the diff. So if you're a mutation tester and see 100,000 unkilled mutations, sometimes a single test can kill 50% of them. So the mutation tester is plain dumb. It just fuzzes your code. It's like not fuzzing an input. It's just fuzz your code. Okay. To run a mutation tester, you need to manage the CLI. I don't have any examples about the CLI here because I wanted to talk about the theory of mutation testing, and it's not really this talk is not really about Mutant itself. It's about what mutation testing is, and I want to interest you, the audience, in trying it out. There are many mutation testers, so I don't want to start with Mutant now because Mutant, all mutation testers are it's a complex topic. So I only can scratch the surface in this format. So I really hope for questions. Are there questions? No questions. Okay. Okay, that's your slide. Yeah, write real unit tests. That's actually an additional nice property of mutation testing. If mutation testing is too slow, you don't have unit tests. That's nothing to argue about. Okay, the test selection, I should have just go forward. This is a test selection slide. Yeah, the isolation one is really interesting. So if you just randomly change your code and execute it, what can possibly go wrong in a dynamic language? So if you have a test that dynamically generates a test a class, or if your code is, if the subject of the code is to dynamically generate classes and put them somewhere into the VM under a constant, it might leak and all later run tests will totally could be screwed up. So we could have artificial dead mutants. So there needs to be sandboxing, and that, especially the sandboxing stuff, that was the reason I wrote my own mutation tester, because Hackle did not have it, and once I had 100% mutation coverage with one test, and so basically that one test had a mutation that invalidated all future tests. So currently I fork before injecting the mutant and measuring the effect. It works quite nice. There are many other strategies, especially when we will go into mutation testing under JRuby. We can probably just build a second runtime to isolate the effects. I'm not really sure. Okay, because there is no silver bullet, you all know. There are really shortcomings of all mutation testers I have to mention here. So there is the problem of equivalent code. If a mutation tester mutates your code in a way it has exactly the same semantics, nobody can rescue you to manually blacklist the mutation, to say, okay, I, as a human, can decide that one should never be in the report again because it's dumb. What's really nice on Ruby, because we have a such dense enumerable API, and most of the equivalent mutants typically occur here, this would not happen mutant. You would just use 1.up to 10, and no mutant would generate an equivalent mutant here. That's really nice property. Okay, so yeah, then we have the infinite runtime problem. I did not solve that currently, and I'm not aware on any mutation tester that has a sane solve to that problem, because if we have a conditional and that conditional controls the loop, and yeah, that loop will never terminate, the mutation test never terminate, it's a halting problem. Nobody can tell you you should count it as killed or not as killed. Currently it does not happen that much because of the enumerable API, because we control the loop execution in a better way than just putting in conditional expressions typically in Ruby. So it's not a big problem currently. And another example, so if someone codes a bug like this and writes a test for 9, or writes a lookup table for 100 integers where the square root is known, mutation testing will not tell you that the implementation is incorrect. So mutation testing can only make sure the coverage between intentions of the tester and the coder are in sync. If someone wants to cheat, he can still cheat. So it's not a silver bullet here. Okay. There is a hunting cheat sheet. It's totally imperfect, but basically it boils down to whenever killing a mutation, think about not adding a test, think about writing simpler code. So if there is a way to avoid a literal do it, if there is a way to reduce syntax, just do it. It results in less mutations and you will be happy afterwards. When to use mutation testing, I can't say. So I have commercial projects on Rails, which are 100% mutation covered. It takes a while. In that project, it proves some value. I have projects where I tried to apply mutation testing and it failed, mostly because we had a legacy test base which far too much remote code execution or inter-process communication, so the setup and teardown times ruined the experience. That's up to the community to decide where mutation testing is appropriate. For all mathematically and algebraic and transformation domains which are self-contained, I can only recommend it. If you want to try mutation testing on your project, use mutation test the classes where money is around. It works. It's a fitting domain. It allows to test something critical, because your revenue calculation, your card calculation, your promotion code stuff, that's something where that should be, in my opinion, be mutation code, because it's our job to do the best to our knowledge. So hopefully you have more knowledge now and run home to your product owner and say, okay, I have more knowledge, I can't stand code without mutation testing anymore. Okay. I would love to see some questions. Yes, the statement stuff.
So, wait for me to get to the slide.
I'm searching.
Yeah, so my question is about this slide. We have two statements, side effect A and side effect B.
Yeah.
How would mutation testing
cover
the fact that maybe side effect A should happen?
It would delete side effect A and run the tests. Statement deletion.
but then you would have to ensure that the tests actually do test the side effect A.
Yes,
with
exactly. You
having-
will notice
Yeah.
a live mutant. You will see in the diff just a removed line, and it will. And you, as a programmer, should identify, hey, why can the mutation tester remove that line without my knowledge?
Okay.
Yeah, please go on.
There are some authors that write that it's not a good idea to aim to 100% coverage, to aim 100% line coverage because it's too expensive. Could you tell us what should you aim for a mutant coverage?
So I personally aim 100%, but that's the loopback effect. So because it's my tool, I try to fulfill the tool's the tool's intention. But I would aim for 100% coverage of core classes. That's if you have a tricky class, if you have the class that, or even a group of classes which is a core of my domain, that should be 100% covered, because it's a great way to really find dead code into the most important business path.
I got a question. How do these mutations of where you're mutating the code?
Where's the guy?
Right here.
Okay.
So you're basically showing basic mutations where you mutate the code, but there's also like practices where you mutate the tests. Like like quick check is the best example of this.
Yes.
Do you have some experience with this, and how do you compare the two?
I tried to use quick chat and I failed with the setup. So I have zero experience with quick chat, but I know it's closely related to mutation testing, and I think we could, when we would have a more introspectable invariant definition, and I'm not talking about RSpec here because RSpec does not have that one. We have to parse the code again, do some assumptions, what on. But if we have introspectable predicates on various states of our objects under test, we could probably do something like quick chat based on mutant, quick check based on
Right.
mutant.
So maybe as a follow-up, do you think Ruby is a language where you can do invariant checking like that sensibly?
In my opinion, yes. Actually, Ruby is the language, to my knowledge, where mutation testing performs best because it involves doing what Ruby is supposed to do, loading dynamic code. So the Ruby runtime, we can all bitch on it because of performance, whatever, but it excels under mutation testing because injecting mutant is nothing more costly than a require, and requires are really common in Ruby. So it's a good optimized path.
Yeah, so you gave an example of a project where mutation testing failed on.
Yes.
Can you give an example of something where mutation testing was very successful? Like you found that, wow, there's a
Okay.
big problem here, or something like that that we can...
I need to include that stuff in the slides. So Dan Kapp, who wrote the Axiom library, mutation covered Axiom, wrote a fuzzer, wrote an SQL generator, wrote the SQL, plugged the fuzzer to generate random mutations on the relational algebra, not related to mutation coverage, but we produced code which was able to run a fuzzer, generate a random relation, serialize it, generate SQL, serialize it, apply it to SQL and to SQLite. We found a bug in SQLite. Yes, so it's actually fixed upstream. I have to include the references into the slides.
More questions? Back there.
Yeah.
Hey, so this is maybe like also like idea. Do you have like any statistics? For example, you can check how many mutants were killed by given test, and also how many tests killed the given mutant.
I only have the first direction you mentioned, so I know how many mutants. I should have included some reports mutant generated, but today I did not finish, so I couldn't update my slides. Yeah, so I know what mutants are dead on a given subject on the whole project under mutation, but I don't know the inverse, and that's basically a shortcoming of me doing the RSpec integration. So we could do that, but in my opinion, we should do something like quick check, and the measurements will become even more better when we know more about the predicates.
Hi, so my question is, Because you already said that it's kind of costly to run those mutant tests. So where do you think they fit in the development process? When should you run them?
I run them locally via I know I should probably write a guard plugin. So I know I changed that class, let's mutation cover it. It will take a minute before I check in. So I have an excuse to take a new coffee or so. But I recommended it to run it on stage 2. So if you have a normal CI setup, a multi-stage setup, so there is a standard unit test, whatever. I run them before my headless test typically. So that's what works best for me, because if identifying a problem on a headless test is much more costly than identifying a problem which gets reported in a diff. So I arranged the chain of tests in the way of how problematic it would be to track down a problem.
Thanks.
Back up here again.
Yeah, no problem.
So I have two questions. The first one is, when you started doing mutation testing, what was the most common, the most common reason why your test failed? So what were the things that were being changed the most often? That,
me not being able to see why specific code could be changed without the knowledge of the test. So it took me a while to learn to infer the connection between the behavior change which was introduced and the test, and why the test does not kill it. So I ended up basically doing the same mutation, just firing up Vim, doing the same mutation in the code, and try to make it dead by hand with my normal TDD cycles. So either I just said, okay, I will keep this mutation if I can't prove it wrong, or I will just find a way to refactor my tests to make them red and then change the code back. And yeah, that's basically at the time I identified Git is really nice. So.
Okay, so my second question is more about these multi-stage testing setups. Part of the content from my talk is being able to switch out different implementations so the test can run faster, and I actually have more multi-stage setups where you have fakes and then real implementations. And what you mentioned was that if you don't have fast mutation testing, you essentially don't have unit tests.
Yeah.
So from your experience, does integrating mutation testing into a workflow encourage you to also separate the concerns more and get to a point where you have a more multi-stage testing environment?
Absolutely, because I identified good code is easy to mutation cover. So I sneaked in mutation testing to various projects already, and I just started as a core classes, 1 class, 2 class, and over the time I realized, okay, I want to have this class mutation cover too, but it was generating shitloads of mutation I could not test. So it was better to refactor the class and then mutation cover it by using the existing tests as an anchor.
So do you do anything without mutation testing now?
No. That's simply no.
Any more questions? No? Yeah.
There was. I saw a hand.
So when you do one mutation and you launch the whole suite, how do you identify the mutants that should change, so they should fail? Because you have probably a lot of tests that pass.
If you use the shotgun approach, all tests are allowed to kill the mutation. Any failed test kills the mutation. So there is no need. It's a really unintelligent strategy. Okay. So for now, mutants default is to use a selective selection. So if you have a mutation on foo sharp bar, only tests which the RSpec meter description foo sharp bar are allowed to kill the mutant, and only that one gets executed to get the mutation test speeds up.
So actually, you launch selectively, not the whole suite.
Yeah, by default. So there are you cannot configure it in mutant because I tend to write open source code only for my pleasure. So that's I'm a little bit egoistic here, but my open source time is limited. So I typically only bring in the features I personally like, and if there is a pull request which adds another feature, I will accept it, clean them up, whatever. But I don't. I know there is lots of demand for more selective selection strategies, but I could not make it currently. No, it's okay.
Yeah. Okay. So my next question is about mocking. In one of the slides, you used mocking as an example. Of,
Mocking?
should receive.
Mocking.
Mocking. Yeah.
Yes,
Should receive
okay.
and all those things. Does mutation testing invalidate the need for mocking?
No,
No.
no, because you need mocking to write a true unit test. Sometimes. Sometimes, in cases where you test a class which does I/O, you need a mock to write a pure unit test.
Yeah.
But I typically prefer to choose to set up units from my objects from my domain to put them in. So I don't think mutation testing hinders or promotes any mocking.
But will mutant also change like method calls, or is it just literal stuff? I mean,
No. It has shitloads of mutation. So So it does. The last time I counted, I had 91 different unique mutations, but I should find a better strategy to enumerate them.
Well, maybe was it one slide back where you have like if input does something? No, okay, maybe I'm thinking of something else. But maybe there was one test or one slide where it said something like should receive.
Yes.
Would,
It was just an example to measure a side effect. You can use any strategy.
yeah. So would mutant also? That test could fail because mutant could change the message being called as well, like the method.
Anything which makes the test fail counts as a killed mutant.
I guess okay. I guess my question is: does maybe you already answered it, but does having mutant invalidate the need for some mocking in a way?
I don't think so.
No.
I don't think so.
All right. Thanks, Markus.
Thank you. Cool.